Welcome to lecture 12 of CAD. In this lecture, we are going to be talking about design of curves. Essentially, we'll touch upon representation techniques and differential geometry of curves. In the layout, we are in the second column here on design of curves. Why is curve design important? Well, it forms the backbone of solid modeling. A network of curves, as you know, would represent surfaces, a set of surface patches forming a closed, simple, and orientable surface represents a solid. This is a concept we have emphasized over and over again in previous lectures. Let's discuss in brief a few traditional methods of curve design. The first one is curve interpolation. Given a set of n ordered data points, xi, yi, I going from 0 to n minus 1, we need to fit a polynomial y equals px, which is a degree n minus 1. We all know from our grade classes and from our engineering first, second, third year classes how to do this. The polynomial will be of the type a sub 0 plus a sub 1 x plus a sub 2 x squared, and so on and so forth. The unknowns will be the coefficients a0, a1 up till a sub n minus 1. As I said before, this is how the polynomial is going to look like. A sub 0 plus a1 x sub 0 plus a2 x0 squared plus a sub n minus 1 x0 raised to n minus 1. This is the polynomial when x0 is used in place of x. Clearly, the left hand side will be the value y sub 0. Likewise, if we substitute x equals x1, the left hand side will be y1, and the right hand side will be a sub 0 plus a1 x1 plus a2 x1 squared, and so on and so forth, the last term being a sub n minus 1 x1 raised to n minus 1. We can keep on substituting. The last equation will be y sub n minus 1 equals the value of the polynomial for x equals x n minus 1, which is a sub 0 plus a1 x n minus 1 plus a2 x n minus 1 the whole square up till a sub n minus 1 x sub n minus 1 raised to n minus 1. These are n equations, n unknowns, and we can solve them. We all know how to solve them. All we need to do is represent this set of equations in compact form and invert an n by n matrix. Notice that matrix inversion is an n cube operation. If the number of equations, that is, if the number of data points is large, the inversion process will be slow. An alternative is the Newton's interpolation technique. This avoids matrix inversion altogether. The trick is to write the degree n minus 1 polynomial slightly differently. The polynomial px is expressed as alpha sub 0 plus alpha sub 1 times x minus x0 plus alpha sub 2 times x minus x0 times x minus x1, the last term being in this series alpha sub n minus 1 times x minus x0 times x minus x1, and so on and so forth, times x minus xn minus 2. Notice that this term is a constant. This term is a constant. This is the term of degree 1. This here is a term of degree 2. The next one will be a term of degree 3. And the last one will be a term of degree n minus 1. Notice also how these terms are arranged. For example, if I substitute x equals x0, all these terms become 0, leaving only alpha 0. If I substitute x equals x1, the first term and the second term remain in the series, while all the other terms, they become 0. This allows to sequentially compute the unknowns alpha 0, alpha 1, alpha 2, and so on and so forth. If we substitute x equals x0, we'll simply get y0 equals alpha 0. As I said before, all these terms will vanish. If we substitute x equals x1, the third term, the fourth term, and so on and so forth will vanish, leaving only the first and the second term. Right here. Alpha 0 plus alpha 1 times x1 minus x0. This will be equal to y1. We already know alpha 0 from before. Using this equation, we can compute alpha 1. For x equals x2, the first three terms remain in the series, while all the other terms become 0. These are the corresponding three terms, alpha 0 plus alpha 1 times x2 minus x0, plus alpha 2 times x2 minus x0 times x2 minus x1. We know alpha 0 and alpha 1 from the previous two equations. Using this equation, we can compute alpha 2. Notice again that these unknowns, alpha 0, alpha 1, alpha 2, they are getting computed sequentially and not simultaneously, as in the previous curve interpolation technique. We can continue with this process and eventually get alpha n minus 1. We will discuss this later, but just briefly, these coefficients alpha 0, alpha 1, alpha 2, alpha n minus 1, they are all called the divided differences. What are the advantages? We do not need to invert an n by n matrix here. Once again, we do not need to solve the entire system simultaneously. And if in case an additional data point xn, yn is added, we do not need to recompute these coefficients. Instead, all we need to do is compute a new coefficient, alpha n. Let's consider an example. We need to construct a polynomial to interpolate through the data points 0, 0, 1, 3, 3, 5, and 7, minus 2, using the Newton's divided difference method. Let me show you an alternative, very easy technique to compute the coefficients. I'll show this on the board. We compute the divided differences or the unknown coefficients column-wise. The first thing we do is we arrange all the abscissa and ordinates into columns like this. The first point is 0, 0. The second point is 1, 3. Third point is 3, 5. The fourth point is 7, minus 2. This value here is y0, and we know that this is the first unknown, alpha 0. To compute the first divided difference, what I do is I use these four numbers and compute the divide difference as 3 minus 0, which is this value minus this value, over this minus this, 1 minus 0, which is 3. Likewise, I can compute the divide difference using these four numbers. How do I do that? It's 5 minus 3, this minus this, over 3 minus 1, which is equal to 1. Next, I use these four numbers here. The divide difference is minus 2 minus 5 over 7 minus 3, which is equal to minus 7 over 4. I'll now fill the subsequent column next. What I'll do is I'll use these numbers and the corresponding interval to compute the next divide difference. This is how. 1 minus 3 over. Now here, I'm going to be skipping this entry and I'm going to be considering this interval here. 3 minus 0, which is equal to minus 2 over 3. Likewise, the divide difference here will be minus of 7 over 4 minus 1 over. Now I'm going to be considering this interval here. 7 minus 1. This is equal to minus 11 over 24. And finally, I'll use these two numbers and I'll use the entire interval, the first entry and the last entry. The corresponding divide difference will be minus 11 over 24 plus 2 over 3 over 7 minus 0. This turns out to be minus 11 plus 16 over 24 times 7. 24, 7. This is equal to 5 over 168. Now, where are my unknowns alpha 0, alpha 1, alpha 2, and alpha 3? In this converging triangle, this is where the unknown coefficients are. This one is alpha 1, this one is alpha 2, and this one here is alpha 3. These unknowns appear on the top edge of the triangle. Coming back to the example, one can also compute these unknowns, the divide differences, algebraically. We know alpha 0 is the same as y0, which is 0. Alpha 1 is y1 minus alpha 0 over x1 minus x0, which is 3. Alpha 2 is y2 minus alpha 0 minus alpha 1 times x2 minus x0 over x2 minus x0 times x2 minus x1, which is minus of 2 over 3. And alpha 3, you can work out the algebra. Y3 minus alpha 0 minus alpha 1 times x3 minus x0 minus alpha 2 times x3 minus x0 times x3 minus x1 over x3 minus x0 times x3 minus x1 times x3 minus x2, which is 5 over 168. We have seen these values before. The corresponding polynomial then becomes y equals 3 times x minus 2 over 3 times x minus 1 plus 5 over 168 times x minus 1 times x minus 3. If I try to move the third data point, 3, 5, to a new location, 3, 2, this polynomial is bound to change. The new coefficients are alpha 0 as 0 the same, alpha 1 as 3 the same, alpha 2 will be now minus 1.1667, and alpha 3 will be 0.1548 using the similar procedure. The new polynomial yn is 3x minus 1.1667 times x minus 1 plus 0.1548 times x minus 1 times x minus 3. Well, how do we see both these polynomials graphically? The curve in red is the old polynomial, and if I move the third point to a new location, the curve in black shows the new polynomial. What do we observe? We see that change in a data point's position results in global shape change of the curve. Remember, we are interested in designing the curves, and we would be more interested in knowing what happens when our design parameters, in this example, the data points, as we would call them later, would change in position. There are a few disadvantages of curve interpolation techniques. We would see more oscillations for higher number of data points. This is obvious. A polynomial of degree n will have at most n real roots. Graphically, that polynomial is going to be intersecting the x-axis at most n number of times. The more the n, the more would be the oscillations. The less the n, or the less the degree of the curve, the better for us. The second point, global change in shape is observed if any data point is moved. In other words, curve interpolation methods do not offer local shape control to a designer. Well, we have an alternative. To minimize oscillations, what we can do is use a lower degree curve. That would mean that we would forego the ability for a curve to pass through data points. Instead, the curve will be very close to them. The notion is to best fit data points with a curve of lesser degree. For example, given a set of n ordered data points, xi, yi, I going from 0 to n minus 1, we best fit them, let's say using a quadratic polynomial, Px equals a sub 0 plus a1 times x plus a2 times x squared. Well, what we do is we would first compute the least squared error. The least squared error is given by capital delta, which is equal to summation I going from 0 to n minus 1 of individual errors delta I squared, which is equal to summation I going from 0 to n minus 1 yi minus a sub 0 plus a1 xi plus a2 xi squared, the whole square. What would this equation mean graphically? Let me explain on the board. Well, I start with the two-dimensional coordinate axis, xy. Let's say we have a bunch of data points here, and we are trying to fit a quadratic polynomial, which would best depict the positions of these points. Let me take any point. Let's say this is point I. Let me draw a vertical. This distance here is xi, which is the abscissa of this point. And this distance, the ordinate of this point, is yi. At x equals xi, the ordinate predicted by this quadratic polynomial is, let's say, yp. Naturally, the error would correspond to this distance, which is yi minus yp. One can either take the absolute value or one can take the squared value. This is delta I squared. Recall that this is a quadratic polynomial. So the predicted value yp for x equals xi will be given as, well, in fact, let me compute the error. This is yi minus yp will be a0 minus a1 xi minus a2 xi squared, the whole square. This distance here, again, is delta I. Naturally, the overall error, capital delta, will be the summation over all the points of small delta I squared. Now, how do we compute the unknowns? A sub 0, A sub 1, and A sub 2. Well, we minimize this error, capital delta, with respect to these unknowns. How do we do that? We go back to basic calculus and we realize that if we treat these unknowns as independent variables, we can compute the slope partial delta over partial A sub 0, partial delta over partial A sub 1, partial delta over partial A sub 2, and make these slopes all go to 0. Let me derive these equations for you on board. So partial delta over partial A0 is given as summation I going from 0 to n minus 1, 2 times yi minus A0 plus A1 xi plus A2 xi square times minus 1, and this will be equal to 0. Let me bring this summation inside and rewrite this equation as summation I going from 0 to n minus 1 yi minus A0 summation I going from 0 to n minus 1 or 1 minus A1 summation I going from 0 to n minus 1 xi minus A2 summation. Let me drop the upper and lower limits here, xi square. This is equal to 0. One can compute partial delta over partial A1 in a similar fashion as summation 2 times yi minus A0 plus A1 xi plus A2 xi squared times minus xi, and this will be equal to 0. Likewise, partial capital delta or partial A2 will be equal to summation 2 times yi minus A0 plus A1 xi plus A2 xi squared times 2 xi. This is equal to 0. Looks like I have made a mistake here. I'm computing partial derivative with respect to A2. So this term here will actually be minus of xi squared. So we have 3 equations, 1, 2, and 3. And if you work out the second and the third equation, try to simplify them, you would notice that you'll have these 3 relations which are linear in the unknowns A0, A1, and A2. So it's a 3 by 3 system we're talking about, which is very easy to solve. Well, let's consider an example now. Construct a quadratic polynomial to best fit the data points 0, 0, 1, 2, 3, 2, and 6, minus 1. We have seen just now how to compute the unknowns, the unknown coefficients of a quadratic polynomial. We'll simply give you the results now. For these 4 data points, the quadratic best fit polynomial is 0.27 plus 1.55 times x minus 0.3 times x squared. If I move this point 3, 2 to a new location 1.54 and retain the locations of all the 3 points, I get a new quadratic polynomial with coefficients minus 0.16, 3.35, and minus 0.58. Let's see the two quadratics graphically. The black curve is the first quadratic equation, and if I move this point to a different location, I get this red curve as a new quadratic function. Once again, we observe that changing the location of any data point affects the shape of the entire curve. Some features of curve fitting. Well, the oscillations get reduced for higher number of data points, which is expected since we're using low order or low degree curves to fit the given set of data points. But we still see global change in shape if any data point is moved. We still do not have local shape control on the curve. What do we learn? Use of low degree curves to avoid unwanted fluctuations, and there is a possibility of the use of juxtaposed piecewise segments to facilitate local shape control of the curves. Let me give you an example on the second point here. Well, all we need to do is we need to consider the given set of data points or control points or design points, as we will call them later, in different subgroups, each of smaller size. And then we can either interpolate or best fit the points in individual subgroups using low degree segments. In this example, we had taken 4 data points in the first subgroup and interpolated them using a cubic curve. The next group is again of 4 data points, again interpolated using a cubic segment. This point here is the junction point, common to both segments. And the two segments form, so to speak, a composite curve. Well, let's say if we try to relocate this point, the shape of the previous segment is expected to remain unchanged. It is a set of continuity conditions at the junction points that will worry us later. Let's now focus upon different mathematical representation techniques for curves. In general, we have explicit equations where a dependent variable y is explicitly expressed in terms of an independent variable x. For example, we have the equation of a straight line from coordinate geometry. Y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1. Well, what happens when x1 equals x2? The line is vertical. The fact that y is non-unique for this vertical line is not very clear using this explicit representation. In fact, this explicit representation cannot handle the condition x1 equals x2. Another case. implicit representation, where independent and dependent variables are expressed together in a function g of x and y equals 0. From this equation, it's not very clear which variable is dependent. For example, the equation of a line ax plus by plus c equals 0, and the equation of a circle x squared plus y squared minus r squared equals 0. If we find the intersection between this line and this circle, the first thing we would need to do is we would need to convert these equations in the explicit form respectively. And further, if there are two real roots, computing those roots will take extra mathematical processing. The third representation is a parametric one, where the coordinates in the Euclidean space x, y, and z are expressed each in terms of functions of an independent parameter u. For example, x is f of u, y is g of u, and z is h of u. F, g, and h are three functions of parameter u. The first advantage we get is that the issue of vertical tangents gets resolved. How? Well, one can simply say f of u is x0, which is a constant, and g of u is equal to u, where u goes from minus infinity to plus infinity. Further, if we have two curves in, let's say, two-dimensional space with functions f1 and g1, both expressed in terms of parameter u1, and for the second curve we have functions f2 and g2, both expressed in terms of a different parameter u2. If we need to compute the intersection between these two curves, all we need to do is say that the corresponding x's are equal and the corresponding y's are equal. In other words, f1 of u1 equals f2 of u2, and g1 of u1 equals g2 of u2. Two conditions will give us values for u1 and u2. The third advantage with parametric representation is that segments can be represented by imposing bounds on the parameter. For example, an arc of a circle. Parametrically, circle is represented as x equals r cosine of theta, y equals r sine of theta, and if we impose bounds on the angle theta, theta 1 being the lower bound, theta 2 being the upper bound, we would be able to represent a segment of a circle or an arc. This is not very much possible using either the explicit or implicit forms. Using parametric representation, the compact vector form of the parametric curve can be written as r of u, note that r is in bold, represents the position vector of a point on the curve, is equal to x of u times I, unit vector along the x direction, plus y of u times j, unit vector along the y direction, plus z of u times k, unit vector along the z or z direction. Bottom line, we prefer to use parametric representation due to its advantages over the explicit and implicit representations. Number one. Number two, we prefer to use low degree curves to minimize unwanted oscillations. And number 3, instead of using a single curve, we choose a set of curves, join them together or juxtapose them together at junction points to form a composite curve which would represent a final design that would either interpolate or best fit the given design points or data points.